Hello everyone, I'm one of the authors of the paper, A Framework and Dataset for Bugs in Ethereum Smart Contracts, Xiaopeng. Now, I briefly introduce our work. I will divide our work into the following six sections to explain. Now, let's begin. The section 1, Introduction. Millions of smart contracts have been deployed onto Ethereum, the largest blockchain that supports smart contracts. The deployed smart contracts cannot be modified for patching the bugs. Unfortunately, similar to traditional computer programs, it is difficult to avoid the bugs in smart contracts. For example, Ethereum has had a very serious smart contracts accident. For example, the DAO. Although recent studies proposed a number of tools for detecting the bugs in smart contracts, but recent studies found that these tools can only discover some kinds of known smart contracts bugs. And another study revealed the major reason for the prevalence of smart contract bugs is the lack of a comprehensive classification framework for smart contract bugs. And although a few studies summarized and classified some kinds of bugs in smart contracts, they have the following limitations. Existing studies do not cover all known bugs in smart contracts. Lack of detailed bug detection criteria. Existing dataset for smart contract bugs are incomplete. So to fill this escape, we make the following contributions. We propose a new framework for all known bugs in smart contracts by extending IEEE standard classification for support-wire anomalies. We design the detection criteria for each kind of bug by taking into account the cause of each bug, the most common form of bugs, and the potential false positives and negatives generated by various detection tools. We construct a dataset of parametric smart contracts which cover all kinds of bugs in this paper. And finally, we use our dataset as a benchmark to evaluate the state-of-the-art smart contract analysis tools. Background. Smart contract. When the conditions specific in the contract are met, all the smart contracts are called. Smart contracts will be executed automatically on blockchain. To avoid abusing the computational resource, Ethereum charges gas from each executed smart contract statement, and Solidity is the most widely used programming language for developing Ethereum smart contracts. Solidity is also a Turing-complete and high-level programming language capable of expressing arbitrary complex logic, and attribute standard classification for software anomalies. It provides a unified measure for the classifications of traditional software anomalies. And the third section is our classification framework. To build a comprehensive classification framework, we first need to collect smart contract bugs. First, we collect smart contract bugs from academic literature and the web blogs and other resources. Second, the open source projects are also our focus, since the open source community plays an important role in the field of software security. Third, since some famous Ethereum smart contract analysis tools can detect smart contract bugs, we sent emails to the authors of this tool asking what kinds of bugs they can detect. And and to continue collector bugs, we developed a program called bug getter, which runs regularly to conditionally collect bug information, and then we merge the duplicate bugs. Uh, And you can find our program in the URL. Uh, and we classify 49 kinds of bugs into the following 9 categories. According to the IEEE standard classification for software anomalies issued in 2010, software anomalies are classified into 6 categories, namely data, logic, description, standard, interface, and syntax. And we do not consider the syntax category because a smart contract with syntax bugs cannot be deployed to Ethereum. And some bugs are specific to Ethereum since these bugs cannot be accurately classified by the standard. We add 4 new categories, uh, namely environment, interaction, performance, and security. Uh, and finally, to help developers and researchers have a clear understanding of the consequence of each bug, we grade the severity of each kind of bug. Uh, First of all, the IEEE standard classification for software anomalies divides the impact of the bugs into the following 4 categories, uh, namely function, performance, security, and serviceability. Uh, then, according to the impact of each bug, we give the severity level of each bug according to the criteria shown on the right. Critical. These kinds of bugs must affect security. High. The level high means these kinds of bugs may affect security or must affect function. The level middle means these kinds of bugs may affect the functionality or must affect performance. And the low means these kinds of bugs may affect performance or must affect survivability. And the section 4. We call our classification and framework and dataset JoJo. JoJo provides examples of each kind of bugs to help smart contract researchers and developers better understand the bugs. JoJo includes 176 smart contracts, covering all smart contracts bugs studied in this paper. For each kind of bug, JoJo provides at least a contract with a bug, a contract that fixes the bug. And we also manually prepare some contracts that may cause existing analysis tools to make mistakes. We call these contracts qualified contracts. And how do we construct qualified contracts? First, the promise. The promise is according to whether detecting a bug relies on its context. We divide the bugs into context-independent bugs and context-dependent bugs. The former can be located according to the specific statements, whereas detecting the latter needs to take into account the context statements of the bugs. So we only create crafted contracts for context-dependent bugs. And we construct crafted contracts through the 3 strategies shown on the right. The first strategy, let me see. Strategy is this strategy divides the statements that causes the bug into multiple statements or multiple functions or multiple contracts. It can effectively reduce the precision of static code scanning tools. The second strategy is providing the statements that can fix the bugs but make the statements invalid or unreachable. It can reduce analysis tools to miss the bug. And the third strategy is using uncommon means to fix the bugs. It can mislead analysis tools to report a false positive. And we collected smart contracts from the following three sources. The first is other smart contract datasets, and the second sample code in the papers on sample code smart contract audit checklists, and the third is we manually develop smart contracts based on the features of some kinds of bugs. The following table shows the distribution of the number of unchanged smart contracts, modified smart contracts, and smart contracts that are developed by ourselves. The section 5 is evaluation. We use smart contracts in individual datasets as a benchmark to evaluate the ability of several smart contract analysis tools. And analysis tools with good ability should be able to analyze as many kinds of bugs as possible, and it should also have good precision and recall rate. So we use three indicators to measure analysis tools: coverage and recall and precision, and then we select and evaluate the tools according to the following two criteria. The first is the tool is free to use, and the second is the tool takes a solidity contract on complied bytecode as input. So according to our criteria, we get 9 evaluated tools. You can see these tools on the right. And this page shows our evaluation results. The figure on the left shows the results of our evaluation, and the right is our findings. The first findings: the coverage of static code scanning tool. For example, Smart Check is usually high, and the coverage of tools based on the control flow or data flow analysis is usually low. And second is when EVM is updated. Due to lack of update and maintenance motivation, the bytecode based tools may not be able to adapt to the new version of EVM, resulting in the limited availability of these tools. However, since bytecode based analysis tools usually use techniques such as control flow or data flow analysis, they usually have higher precision. Mr. and Slither are generally regarded as the most effective tools, and the crafted contracts can make these 9 tools produce more false positive and false negative. Although most analysis tools currently use techniques such as control flow or data flow analysis, static code scanning tools are still valuable because these tools relatively easily to develop. Because it is relatively easy to develop static code scanning tools, and they can detect more kinds of bugs with better coverage. And the final finding is there are still 10 kinds of bugs that cannot be detected by 9 evaluated tools. And the final is our conclusion. By collecting all known bugs in smart contracts, we classify them based on the extension of attribute standard classification for software anomalies and give the detection criteria for each kind of bug. Moreover, we construct a comprehensive dataset of valuable smart contracts that covers all these bugs and obtain the new observation by using this dataset to evaluate the state of the art tools for analyzing smart contracts. In future work, we will study how to formally define detection criteria. And thanks. Uh, and the left URL you can find our dataset, and the right on the right URL you can find our paper. Thanks.